Hello and welcome to Diplomatic Derivatives. In today's video, we're going to continue applied mathematics, where we are going to talk about the linear combination of vectors. Now, in one of the previous videos, we have completely covered vector addition and subtraction as well as scalar multiplication, along with, most importantly, the head-to-tail rule. So the link to the video is in the description box below. Make sure you understand that concept. It's also a very simple concept, along with this concept, which is very easy as well if you understand that perfectly. So before moving on, make sure you check that out. Now we'll see what the linear combination itself is. Now, a linear combination is a fundamental concept in linear algebra used to build new vectors from a set of existing vectors by scaling and adding them. So what you will be having is you will have or you already have some existing vectors, right? Using those vectors, you're making new vectors. All right. Well, how do you do that? By scaling and adding, right? So it's a very basic concept. It's basically something can be written as in terms of another thing, right? So you have two standards. You have, let's suppose, vector v1 and you have vector v2. And using these vectors, you make the rest of the vectors within a given space. How do you do that? You either scale. So there are two things that you're going to do. You're going to scale and then you're going to add. All right. We'll see how that happens. Let v1, v2 till vn be vectors in a vector space, and a1, a2 till an be scalars, that is real or complex numbers, right? You have a space. That space, let's suppose we just draw the space, okay? Inside that space, you will have multiple vectors, okay, in different directions. All right, and then you have certain scalars, that is a1, a2 till an. We don't know the exact number of vectors and we do not know the exact number of scalars. So we just assume till n. Then the expression u is equal to a1 v1 plus a2 v2 till an vn is the linear combination. So what you're doing here is you have this first thing. If you focus on it, you have vector v1 and you are scaling that vector. So as we saw in that video where in vector addition and subtraction and scalar multiplication, we saw how scalars are multiplied with vectors. So they if the scalar is positive, it will increase the magnitude of the main vector. If the scalar is negative, it will reverse the direction of the vector. Okay, so that's scaling, right? So this is the first thing that you're doing. You are scaling. In this linear combination, you are scaling. Also, you are adding. So first you scale and then you add. Add it to what? The next vector, which is a2, v2. So a2 is the scaling part and v2 is the vector. And this you keep doing till an, vn. So it depends on the number of vectors. Depending on the number of vectors, you will be scaling and adding, right? That's the linear combination of vectors. Okay. So this is linear combination of vector v1, v2 till vn with coefficients or weights, that is a1, a2 till an. Okay. We will see this with the help of an example. First is geometric interpretation. Same thing. Suppose you have two vectors v1, also not just in terms of real numbers, you can also represent vectors as matrices. Okay, so you have v1 which is 1 0 and v2 which is 0 1. Okay, we will draw them as well. Make sure you keep drawing the vectors so it's easy for you to understand and also perform the addition, that's head to tail rule. Okay, because once you do that, once you have the image in front of you, things become easier. Any vector which is u equal to ab in 2D can be written as u is equal to av1 plus bv2. So basically v1 is in the x direction, okay, and v2 is in the y direction. So this one is v1 and this one is v2. Now how did you get this? You got it by the head to tail rule. So according to the head to tail rule, the addition of vectors is done by what method? First you draw the first vector, then so we're going to draw the first vector, then you will draw the second vector, okay, and the resultant vector is from the tail of the first vector to the head of the second vector. So that's your resultant vector. All right. So with the help of the head to tail rule, you created the resultant, right? And basically performed the linear combination. Okay, so you're moving A units in the X direction and B units in the Y direction. So what you're basically doing is, in the linear combination, you are scaling and then you are adding. Okay, remember, linear combination is two things. You will scale and you will add. Okay, that's linear combination. So you're moving A units in V1 direction and B units in the V2 direction. All right, now let's see an example. V1 is equal to 1, 2 and V2 is 3, 1. Okay, now consider the linear combination that's given to you is U is equal to 2V1 plus 4V2. So you are scaling V1 by 2 units and you are scaling V2 by 4 units. Okay. Now, in place of V1, you write 1, 2, and in place of V2, you write 3, 1. Now, you know how to perform this. 2 1s are 2, 2 2s are 4, you get 2, 4, and 4 3 are 12, 4 1s are 4, you get 12, 4. Now, you add the matrices, you get 14 and 8. So, U is a linear combination of V1 and V2. You basically wrote this new vector, which is vector U, in terms of V1 and V2. So basically you go back to the actual definition of linear combination, which says that from given vectors you create new vectors. So from V1 and V2, so what are our given vectors? Our given vectors are V1 and V2. From these two vectors you created a new vector, which is U, through the linear combination. So basically you're writing U in terms of V1 and V2. Okay, now we are going to understand a few terms that are related to linear combination, why linear combinations matter, and this can come as part of MCQs, where you'll be you'll be asked some definitions related to linear combination or anything. So this is helpful for that. Now, first term is span. Set of all possible linear combinations of set of vectors is called their span. If the span of V1 and V2 covers the entire space, then any vector in that space can be expressed as their linear combination. Now, what does this mean? That in the previous slide where we saw the X and Y axis, and we had one vector over here which was V1, and you had another vector over here which was V2, and then you made one of the resultant vector. Okay, now let's suppose the space that we are talking about is this triangle. Okay, this is the space, and inside this space you will have certain vectors, right? So you have maybe one vector over here, one vector here, and so on. Now V1 lies on one edge of the space, V2 lies on the other edge, so the resultant lies on the third edge, right? What is happening? V1 and V2 along with the resultant have covered the entire space, right? So what happens is, now all the vectors that are lying inside this space can be written as a linear combination of these two vectors V1 and V2. Okay, so this is known as span. So set of all possible linear combinations of a set of vectors is called their span. Okay, I hope it's clear. Now, linear independence. Vectors are linearly independent if no vector in the set can be written as a linear combination of the others. So let's suppose there is one vector over here, and that cannot be written as a combination of any other vector. So it's linearly independent. It is on its own. It does not depend on any other vector. Okay, because over here we see that U is obviously dependent on V1 and V2, right, for its existence. A linear independent vector is something that is not independent on anything. So it exists on its own. Okay. Basis. A basis is a set of linearly independent vectors whose span is the entire space. So basically, you won't have any vector that's having a dependence on anything else, right? So it's a set. Basis is basically a set of linearly independent vectors whose span covers the entire space. Okay. These things can come inside the MCQs part. All right, so that's it for this video. I hope it was clear. You basically just try to understand the main concept. You're in linear combination, you're just scaling and adding given vectors to find new vectors within a space. That's the basic understanding of this. Thank you for taking your time and trying to understand this concept. We'll be moving forward to future concepts, also performing certain exercises in the next video. So make sure you check that out. Also, we'll be moving on to scalar and vector products. So that's also a very important part, which will give rise to, cross products and stuff like that. So make sure you stay tuned for the future videos. And that's all for today. Thank you. Take care. Bye bye.